Okay, now we should see it in the correct view. I apologize for that. Yes, so thank you very much for the introduction. Very happy to be here. I'm going to say, please, if you have questions, feel free to put them in the chat as I go. This is going to be, I think, maybe a little bit of a different talk in the sense that it's a little bit of a review. I know a lot of us know, about graph neural networks, about graph representation learning, but my goal today is to discuss a little bit of the history and then get to a little bit of the theoretical foundations of graph neural nets and then highlight based on these theoretical foundations some open problems that we have from kind of a theoretical perspective, and then maybe time permitting, I'll discuss one or two approaches that my group has been thinking about in terms of how to address these things. So it's kind of one part new work, one part tutorial, and one part theoretical investigation. Okay, so obviously what we're interested in is this task of learning on graph structured data. And just to make it clear what kind of data sets I'm thinking about when I talk about learning on graph structured data, I'm thinking about things like doing friendship recommendation in social networks, trying to do automated fact prediction in knowledge graphs, trying to do things like computational drug design using biomedical networks or by analyzing the graph structures of molecules. There's also many really exciting applications of using graph representation learning for things like analyzing the syntax of language and code, and even looking at networks of neurons as being graph structures. And so this idea of deep learning on graphs or graph representation learning has really seen I think it's fair to say, an explosion of interest in the past few years. So as one metric of that, I'm showing web searches for recurrent neural networks in red, graph neural networks in blue. And what you can see here is that we're really seeing the interest, at least as reflected in Google search trends, of graph neural nets starting to approach their dominant counterpart of the traditional RNN techniques. So as I mentioned, what I want to do today is first give a brief history of graph representation learning. Part of this is setting the stage for part two, which is a discussion of two theoretical paradigms that we can use to understand graph representation learning. And then following that, I'm going to build on this theoretical exposition to discuss three critical open problems, and then time permitting, maybe discuss some ideas I have about how to tackle some of these open problems. And as was alluded to, this is content that is largely based on my book. Actually, I shouldn't say it's forthcoming. I apologize. I thought I had updated that. The book is now out. There is a draft available on my website. For those of you who are curious in terms of the differences between the freely available draft on my website and the physical book, I would say that if you're just interested in the content, you're okay looking at the freely available draft. It's there's definitely some nice images and things like that in the published version, but all the critical detail is there in the one that you can get from my website. Okay, so beginning now with this question of a brief history of graph representation learning. So I think what you can view the goal of graph representation learning as is really there's two problems that we're typically interested in. And maybe this is an oversimplification, but at least this is how I'll think about it today. So the first problem is the problem of, can we map a node to some useful low dimensional representation? What useful means is going to depend on the task, but as is often the case in a representation learning, we maybe want to do this in some kind of task agnostic way, right? So we want to have some way of mapping nodes to vectors or mapping entire graphs to vectors. So we want to be able to have useful, ideally low dimensional representations of graph structured objects. So we might wonder why graph representation learning is hard. Of course, we have convolutional neural networks for images or grids. We have recurrent neural networks for things like text or sequences more generally. But the challenge is that graphs really don't have this geometric structure that we see with simple grids like GNNs or simple sequences, as in the RNN case. And to be a bit more precise, the key challenges with graph structure data, and these are issues that'll kind of return when we start talking about some of the theoretical connections for GNNs. So it's first off, there's this complex geometric structure. So when we're looking at graphs, there's no straightforward notion of things like spatial locality, right? When you're talking about doing a convolution on images, right, we can really think of this as moving this patch, shifting it around on this grid. But when we're thinking about general graphs and thinking about, okay, which nodes are close to other nodes, things can get very like, wacky to say the least, right? So you can have graphs where every node is a neighbor of every other node, right? You can have graphs where one node is connected to every other node, but those nodes are all disconnected from each other. So you can have a star graph, right? And when you think about these sorts of complex geometric or topological structures, it's really hard to think of notions like spatial locality and these notions of straightforward geometry that we're used to in a typical Euclidean grid space. Another really big challenge with graph data is that it inherently has symmetries. So there are inherent symmetries in graph data that lead to non-unique representations. So in particular, if we're trying to learn a function that say maps a graph to a low dimensional representation, so say we're trying to map an adjacency matrix, and I'll generally be representing graphs as adjacency matrices denoted by A. If we want to have a function that maps adjacency matrices to low dimensional vectors, this function must be invariant to node permutations. So what I mean by that is if we permute the adjacency matrix, then applying our representation, our deep learning, whatever kind of F function we want to have, we should get the same output no matter if we permute the adjacency matrix. The order of nodes in the adjacency matrix is just an arbitrary decision that we make. And this means that there's an inherent symmetry that we must account for in our learning. There's also another symmetry if we're trying to learn node level functions. So if we're trying to learn a function that maps a graph or an adjacency matrix to low dimensional embeddings for all the nodes in this graph. So now we're going to try to map to V or N different embeddings. These functions have to be equivariant, meaning that if we're going to apply some permutation to our input adjacency matrix, the output representations that we get are just permuted in an analogous way. So what I mean by this is that if I apply some permutation to my adjacency matrix, so now the node that was in row 1 in the adjacency matrix is now in row 5, what I get as output is the same set of embeddings, just permuted in an analogous way. And now this may seem like a trivial problem, this issue of, okay, well, adjacency matrices are non-unique, what's the big deal? But in fact, this issue, these symmetries, make graphs computationally challenging objects to work with. So in particular, even determining whether or not two graphs are the same. So you give me two adjacency matrices, A1 and A2, and you say, are these the same graphs? This is computationally hard. The mathematical question here is the question, does there exist a permutation matrix such that the adjacency matrix of graph 1 equals a permutation of the adjacency matrix of graph 2? And if you look at this optimization problem, it does look a little tricky because they're trying to find a minimization over the set of all permutation matrices. And that can sometimes be a tricky thing to do. Right? So visually, what we're trying to do is I'm given two graphs and I'm trying to figure out, is there a bijection between the nodes in these graphs? This problem is what's called NP indeterminate. It is not NP hard, but it is believed to be computationally difficult and known to be as computationally hard as trying to factorize integers. So graphs are tricky because they have these symmetries, and these symmetries mean that even knowing whether or not two graphs are the same is a problem that is probably not polynomial time solvable. Okay, so that's a little bit about graph representation learning, why it's interesting and why it's hard. I'm now going to talk quite briefly about the core methods in graph representation learning that have got us to today. So the classic approach that people worked on when they were trying to do representation learning on graphs is what I'll call the node embedding approach. So here, the goal is essentially to encode nodes and typically just using a embedding lookup function. So we just have a embedding matrix where every node has its own row in that embedding matrix. We're trying to optimize that embedding matrix so that the embedding space reflects some notion of similarity in the original graph. So for example, we want the embeddings of two nodes to be similar to one another or to have a high dot product if these two nodes, say, tend to co-occur on random walks, which is the technique used by algorithms like deep walk and node to vec. Now, These traditional node embedding techniques, so things like deep walk, node to vec, line, and so on, they were very powerful. I think in a lot of ways they were, responsible for initiating the renaissance, as you can call it, of graph representation learning and graph neural nets that we've seen over the last 5 or so years. But these techniques had limitations. So in particular, when you're working with these traditional node embedding algorithms, we learn one parameter vector for each node. So we have an embedding vector, a unique embedding vector that we're optimizing for each node. And this means the number of parameters that we need in these algorithms is linear in the size of our graph. So as our graphs grows, our model grows. And that's problematic because it means that we need to add more memory, add more parameters as we add more nodes in our graph. A related issue is the fact that these techniques, pardon me, are what we call inherently transductive. And what I mean by this is that if we're using an algorithm like deep walk or like node to vec, these algorithms cannot generate embeddings for nodes that were not seen during training. So if our data set's evolving over time, or if we have a new graph that we want to get embeddings on, we have to rerun the training algorithm. There's no inference, there's no inductive capability for these techniques. And lastly, these traditional node embedding algorithms do not naturally incorporate node features. So many, if not most graphs have some kind of feature information that we can leverage. If it's a social network, maybe there's user profiles. If it's a protein network, maybe there's information about the proteins related to their expression profiles and so on. And traditional node embedding techniques don't naturally take into account this kind of feature information. So an extremely important innovation that happened over the past, say, 5 or so years was the innovation of graph neural network techniques. So to contrast graph neural nets with traditional node embeddings, the key idea is that whereas traditional node embeddings just learned a big embedding matrix where every node had its own, say, column in this embedding matrix or row, instead, with graph neural networks, we assume that our way of encoding nodes into low dimensional embeddings is actually a complex deep neural network that depends on the structure of the input graph and that uses the node features in order to generate these representations. So I often like to show this image to illustrate how a basic graph neural network works. So the idea is that if we're trying to generate an embedding or a representation of this target node A, the way that we do that is we aggregate information from A's local neighborhood using neural networks. So here, node A, to get its representation at what we call the second layer of this graph neural net. This is going to depend on information that A is aggregating from its neighbors, nodes B, C, and D. And this information A is aggregating from its neighbors is aggregating information from the previous layer in the graph neural net. Then the information at this layer in the graph neural net, at layer 1, in turn depends on information that these nodes are aggregating from layer 0. And so finally, when we get down to layer 0, the initial information that we're using to seed this computational process is actually just the initial input node features. So at the end of the day, the representation for node A is essentially an aggregation of the feature information, in this case, from this node's 2-hop local neighborhood, because here we're using a 2-hop graph neural network or a 2-layer graph neural network. Mathematically, a basic GNN can be written as follows. So what we do is we initialize our layer 0 embeddings as being equal to our node features, and then our kth layer embedding of a particular node is going to be a nonlinear function of the sum of the information from the node's neighbors in the previous layer, so their previous layer embeddings, as well as the previous layer embedding of this node itself. We're then going to multiply these things by some learnable or trainable parameter matrix W, and all of this is going to give us our updated representation. So in terms of the advantages of GNNs, right, first off, we have that the number of parameters is independent from the size of the graph. So this is the fact that the number of parameters in the GNN layers depends only on the dimension of the feature inputs and how large your hidden dimensions are. GNNs are also inherently inductive. So after I train a GNN, I can use it to generate embeddings on unseen data at test time. And of course, GNNs naturally incorporate feature information. So we're treating feature information at nodes really as first-class citizens. Now, GNNs have been generalized substantially in recent years, both in my work and in others. So one of the more general ways we can think about GNNs is instead of having the specific equation I showed earlier for a basic GNN, we can have this generalized message passing idea. So here we're saying that the updated node embedding for a node U depends on information that we're aggregating from this node's neighbors. So we often call this the message that we're aggregating from this node's neighborhoods. And then we're combining this neighborhood message information with the node's previous layer embedding using some kind of update function. So there are many ways that we can actually generalize these different operations. So for example, we can use attention networks in order to aggregate information over neighbors. I also proposed in 2017 in my graph stage work, some generalized aggregation approaches. And this graph stage work was also where I started to think about this generalized notion of neighborhood aggregation. On the side of updates, so how we actually do this update process, we can again generalize this in many ways. So we can do update operations based on gated recurrent units. We can add update operations that have a residual style. And there are many, many proposals in this space. So for example, the talk by Stephen Bach, and then in the previous session was another example of how in that case we can generalize some of these aggregation operations, say. So there's been, I think it's fair to say, dozens, probably more than dozens, maybe more than 100, proposals in terms of how we can generalize aggregations and updates in GNNs. And that's really gotten us to where we're at today. Now, in terms of impact, just to take a step back and think about what graph neural networks have done, where they've seen a lot of success. I think one of the most important impact areas for graph neural nets has been in computational drug design. So we can do things such as combining reinforcement learning with GNNs to search for candidate drugs. So for example, there was a really fantastic paper in Cell last year demonstrating that GNNs could be used to predict novel antibiotics. And the idea here is that we're using GNNs to generate representations of molecule graphs. So here we generate the node embeddings, and then we aggregate all these node embeddings together as a representation of the whole molecule. And then we can predict properties of these molecules based on their embedding. And we can then combine this property prediction approach with techniques from reinforcement learning to even try to search over the space of molecules to find useful, say, drug candidates. And this is very exciting. It can be used for drug design, also for drug repurposing. And for example, an initiative at my institute here at Mila called the Lambda Zero Initiative. There's also a related initiative called Recover that we've been running. Has actually been applying these techniques to try to find drug candidates for COVID-19. Another really big impact area, if we're looking at where graph neural nets have had a big impact in practice, is recommendation systems. So here I'm showing one example from my work. This is a 2018 paper that was a collaboration with Pinterest, where we used the graph stage algorithm, so one of these specific graph neural network techniques, in order to power the recommendation system at Pinterest. This was scaled up to graphs with billions of nodes, something that really wouldn't have been feasible with more traditional approaches. And we were able to actually get substantial gains in terms of things like A/B studies and offline evaluations, in terms of the performance and the quality of our recommendations. So GNNs have risen a lot in popularity, but they've also had really important and major real world impact. That now brings us to the theoretical perspectives on GNNs. So there's been, I think, a great deal of work pushing GNNs forward in terms of the types of algorithms that we have. But now I want to take a moment to talk a little bit about the theoretical underpinnings. And again, this is largely content that comes from my book, which is a combination of new things that I've noticed in my book, as well as a synthesis of existing theoretical work that is out there. So I want to ideally go over two dominant theoretical paradigms that we can use for understanding GNNs. The first, and the one I'll spend a little bit more time on, is the idea of analyzing graph neural nets from the perspective of signal processing. So thinking of graph neural networks as being generalizations of convolutions to non-Euclidean graph data. The second is analyzing GNNs from the perspective of graph theory and the notion of isomorphism testing. And I alluded to isomorphism testing in the first few minutes of this talk, but we can think about GNNs in terms of their power to distinguish isomorphic graphs. Okay, so starting first with this idea of relating GNNs and graph convolutions. So the intuition, I think if we first think about a graph neural network on a simple grid graph, right? What we're doing is we're aggregating information from local neighborhoods. And what this looks like is really akin to a symmetric center surround convolutional filter. So every node is aggregating information from its local neighborhood. We're doing this aggregation, I should say, in a permutation invariant way. And that's necessary because of these symmetries that I mentioned earlier in the talk. So these aggregation functions that we're using to aggregate our node neighborhoods have to be permutation invariant in order to satisfy the symmetries of graphs. But if you think of this idea that, okay, a graph neural net on a grid graph looks a lot like a center surround convolution, we can actually take this intuition and theoretically ground it and say that graph neural nets can actually be derived as a generalization of convolutions to the graph domain based on what's called graph Fourier analysis. And now we'll have a quick crash course in graph Fourier analysis, which I think is really interesting and honestly, I think really important for people who are working in this space to understand. So first off, we're going to define what's called the Laplacian operator for a graph, also called the graph Laplacian. Here, I'm defining what's called the symmetric normalized Laplacian because the math's a bit easier to work with this particular variant, but there's other variants of the Laplacian that we can derive things from. How we define this Laplacian is that it's the identity matrix minus a symmetric normalized version of the adjacency matrix, where this A sim is essentially the adjacency matrix, but where we've normalized it for the node degrees in a symmetric manner. How we can interpret this Laplacian matrix is that if we were to take a signal on the graph, where a signal is essentially a vector where we have one value at each node on the graph, so every node has some value, if we multiply this graph signal by the graph Laplacian, and then we look at an entry in this output, so we take a vector x, multiply it by L, and look at the value for a particular node U, this actually corresponds to the difference between the signal at that node and each of its neighbors, normalized by their degrees. So what the Laplacian does is a difference operator. When we apply the Laplacian to a vector of node features, it gives us the difference between those features at each node and its neighbors. And in fact, the graph Laplacian is really a discretized analog of what's called the Laplace operator on Euclidean space, or actually what's called the Laplace-Beltrami operator if we're looking at general manifolds. And what this Laplace operator is it measures the divergence of the gradient of a function. I think the intuition is the best thing to think about here, and that is that the graph Laplacian measures the difference between some signal at a node and its local neighborhood, so all of its neighbors. The Laplace operator measures how much a function or a signal changes from a node and an infinitesimal neighborhood around that node. So both of these functions, which are just different versions of the same thing, one is discrete and one is more continuous, these operators measure how much a signal differs between a point and its immediate neighborhood. So this gives us a connection between this Laplacian operator on graphs, this matrix that we can define, and this function, this operator that's more general and known as the Laplace operator. The reason why this is important is because the Laplace operator has some very, very important properties. So if we're looking at the Laplace operator in Euclidean space, and we look at the generalized eigenfunctions of this operator, they are actually the Fourier modes. So the generalized eigenfunctions of the Laplace operator are essentially the roots of unity. They are the sinusoidal plane waves. And what this means, the key connection here, is that Fourier analysis, so when we're trying to decompose a signal in Euclidean space as being the superposition or as being the combination of a number of different sine waves, this is equivalent as representing a signal in Euclidean space in the eigenbasis of the Laplace operator. So whenever we're doing Fourier decomposition, one way of looking at this, and there's many different ways of looking at this, Fourier analysis is a very rich space, but one way of looking at Fourier analysis is that when we're decomposing a signal into its component sine waves, we're essentially decomposing a signal and projecting it onto the eigenbasis of the Laplace operator. So now, based on that idea, we can define a graph Fourier transform by representing a signal on the eigenbasis, which in this case would be eigenvectors of the graph Laplacian. So in particular, a graph Fourier transform of a signal on a graph is just the multiplication of that signal by the eigenvectors, actually the transpose of the eigenvectors of the Laplacian matrix. The inverse graph Fourier transform just multiplies by the eigenvectors themselves because these are unitary matrices, those are inverses of one another. We can then define a graph convolution as being element-wise multiplication in the graph Fourier domain. Again, a convolution in Euclidean domain is element-wise multiplication in the Fourier domain, doing the same thing in graph space. So the convolution of a signal on a graph by a filter f corresponds to taking the graph Fourier decomposition of both of these, taking their element-wise product in graph Fourier space, and then we can come back. And another way of writing this down is that we're taking the Fourier transform of our signal and multiplying it by some diagonal matrix. And in terms of key interpretation intuitions here, the Laplacian eigenvectors, they correspond to our Fourier basis. And similarly, the Laplacian eigenvalues, the eigenvalues of our Laplacian, they're the graph analog of different frequencies. Okay, so what does all this graph Fourier analysis actually have to do with GNNs? So in practice, we can define graph convolutions. So one way of actually coming up with valid convolutions on a graph is by taking any polynomial of the normalized adjacency matrix. So in particular, if I take any polynomial of the normalized adjacency matrix, that can actually be simultaneously diagonalized with the graph Laplacian. And this fact implies that when we multiply a signal or some node features by a polynomial of the adjacency matrix, this is equivalent to multiplying the graph Fourier transform of that signal by a diagonal matrix, which is equivalent to element-wise multiplication, and then performing an inverse graph Fourier transform. So to put in another way, anytime we multiply some node features by a polynomial of the adjacency matrix or the normalized adjacency matrix, this is mathematically equivalent to doing a convolution on this graph in a very precise mathematical sense. From an intuitive standpoint, this makes sense. When we multiply by a polynomial of the adjacency matrix, we're taking this signal at each node, and every node is getting a new representation, which is some function of the signals in its local neighborhood. So if we're using a low order polynomial, we're going to be emphasizing just looking at information in this node's local neighborhood. We would take a higher order polynomial. That means we're gathering information from further and further reaches of the graph. So you can think of the spatial view here as we're aggregating information from local neighborhoods, but really this is a precise mathematical graph convolution. And again, the key idea here being that multiplying by a polynomial of the adjacency matrix is a valid graph convolution. And what's interesting here is that the neighborhood aggregation that we do in a basic GNN, and most GNNs, at least if you squint, have this particular style where one of the key things that we're doing is we're summing or aggregating over the nodes within a particular node local neighborhood. So to get the representation of a node U, we're looking at the nodes within its neighborhood. And that corresponds to a multiplication by the adjacency matrix. So when I show that initial image of a GNN where it was aggregating from local neighborhoods, each one of those aggregations is really a multiplication by the adjacency matrix. And this means that many, but not most, graph neural nets can really be viewed as a combination of simple graph convolutional filters, linear projections, and nonlinearities. So very much like convolutional neural networks in vision, but here we're doing graph convolutions rather than standard Euclidean convolutions. Okay, that was a crash course in graph Fourier analysis. I want to quickly talk about graph neural nets and graph isomorphism. So this is the other perspective on GNNs. So this idea of looking at GNNs as corresponding to convolutions is not the only theoretical perspective that we can use to analyze GNNs. The other idea comes from the fact that GNNs are very closely related to a very classic isomorphism testing algorithm, which is called the Wishfire-Lehmann or the WL test. So the key idea with this WL algorithm is that in order to test whether or not a graph is isomorphic to another graph, we can do this by trying to come up with a labeling, a way of representing this graph using a discrete feature vector that follows the following algorithm. What we do is we start off by labeling every node with a color that corresponds to that node's degree. Then for every node, we're going to give an updated representation for that node that corresponds to the set of colors in that node's local neighborhood. And then we iterate this process again. Now we're going to get new labels for all of our nodes that correspond to the set of labels from the previous iteration in this node's local neighborhood, and so on. And the key idea is that in this WL coloring algorithm, a very classic algorithm that's over 100 years old, the idea here is that we initialize each node with a discrete label. Then for each node at each iteration in this algorithm, we replace that node's label with a new label that is a hash, so a discrete hash of the multi-set of labels in that node's local neighborhood. GNNs are actually the same thing. They're just the continuous version of this. In GNNs, we initialize each node with a continuous embedding, and then for each node at each iteration of our GNN, we're getting a new embedding for that node that is a neural network function of the set of embeddings in that node's local neighborhood. And in fact, this connection between GNNs and this WL test is not just intuitive. Like the connection to convolutions, there's a precise mathematical relationship. So in fact, if we assume that we're using a basic GNN architecture, we can theoretically prove that there exists a parameter setting for this basic GNN such that it is just as powerful, so equally powerful, as this WL test, this classic isomorphism testing algorithm. And we can also prove things the other way around. So we can prove that GNNs are no more powerful than the WL test, presuming that we're using an arbitrary differentiable update function and an arbitrary differentiable permutation invariant aggregation function. So GNNs, at least almost all GNNs we use in practice, theoretically from a worst case representational standpoint, are equally powerful as this traditional isomorphism testing algorithm. Okay, in the last couple minutes that remain, I just want to talk a little bit about limitations and open challenges that come from some of this theory. So first off, one of the major challenges we have right now in graph representation learning is trying to find ways to develop graph neural networks that actually go beyond this WL hierarchy. So trying to come up with graph neural nets that in a constructive and useful way are more powerful than the WL test. We do have GNNs that are more powerful than the WL test, but I think we still haven't broken out of this WL hierarchy and found new ways of thinking about the power of GNNs that can push us maybe into the next better paradigm. A related problem, and something many of you have probably heard about, is this issue of over-smoothing in graph neural nets. This is an empirical problem. The issue is that GNNs, especially GNNs with many layers, tend to produce over-smooth representations where basically all the node embeddings start to look identical. There's a theoretical explanation for this over-smoothing problem. The issue is that higher order polynomials of the adjacency matrix, which is what we get when we build really deep GNNs, these magnify the influence of the dominant eigenvalues. So we take really high powers of the adjacency matrix, we get a matrix that's dominated by the larger eigenvalues. And these correspond to low pass filters, i.e. low frequency information in the graph Fourier domain. And a really exciting and open problem, some things that my group is currently working on, is trying to design more complex, more powerful kinds of GNNs that actually do more interesting kinds of signal processing than just looking at low pass filters. Lastly, I want to bring this all together by just mentioning another limitation here, which is connected to these other two. And this is what I call the bottleneck of message passing, right? So when we're getting the representation of this node A here, this is information that we're aggregating from its neighborhood, but what we end up in terms of the computational structure of a GNN is a tree structure. And as we try to aggregate information from further and further reaches in the graph, so as we add more layers to our GNN, we're aggregating information from exponentially more and more neighbors at the furthest depths. And this means that when we're trying to get information, say from one node that's 2 hops or 3 hops away to this node A, that can require that we're passing information, that we're squashing through all of these different exponentially reduced tree layers. And it can be really hard to actually transmit long distance information in GNNs because of this tree structured bottleneck. And in fact, it is my belief, in my opinion, that one of the most important challenges that we have for GNNs is trying to break this computational bottleneck. And I think more importantly, I really think that these three challenges I mentioned, right? So going beyond the WL algorithm, trying to understand how we can break this bottleneck of message passing, and trying to understand how we can go beyond just simple low pass convolutions. In my opinion, these are all just three different instantiations of the same underlying limitation that we have because of the current paradigm of how we design our graph neural nets. So I'm pretty much out of time. I do want to just quickly mention, one of the things. I'll just mention one of the algorithms that I've been thinking about to try to break this. So one of the things that I've been working on with some collaborators is an idea of thinking about how we can define directions over graphs. So one of the issues that makes graph neural nets a lot less powerful in some ways than general convolutions, and why we're stuck with these low pass filters, is that we have no notion of asymmetry in the convolutional filters that we can define. Part of that is that we have no notion of global direction in graphs. There's no notion of north or south. And this is due to the inherent symmetry that we have with graph data. But the idea that we had in our work is that we actually use the eigenvectors, actually the gradient of the eigenvectors of the Laplacian, to define canonical global directions over graphs. And these actually define really natural directions. So I'm showing here, for example, in this Minnesota roadmap, that if we look at the directions specified by the gradient of the eigenvectors, they give us kind of north-south, suburb versus city, and east-west directionalities that we can then use to define, in some ways, more traditional types of convolutions. And we show that using this approach, we can have methods that are more powerful than the WL algorithm, and also that generalize convolutions on grids in a more powerful way. So we can represent any kernel that we could have in the image domain using this approach. So this is just one, just a teaser in terms of an exciting direction. And I listed the paper down here at the bottom. So with that, I will conclude, thank my funding agencies, all of my students, and hopefully we have time for maybe one or two questions.
So thank you for the exciting talk. So I have a quick question. So I was curious as to how effective were the sampling strategies in handling the bottleneck of message passing?
Yeah, so these sampling strategies are useful to handle it in some ways, but the issue is that they don't. So say we want to be able to pass information between two nodes that are at distance 5 apart or away from each other in the graph. So the shortest path between them is 5 edges. So sampling can reduce the bottleneck, but it can't guarantee that we're necessarily going to get information from that node unless we have some way of learning how to sample in an intelligent way. So one of the directions that we also are examining in our group is, can we kind of learn which neighbors to sample so that we can ideally be able to pass these informative long-range messages. So just uniform random sampling reduces this bottleneck issue in some ways, but it doesn't allow us, it's kind of naive, right? We don't really get to know what information we get from the long-range parts of the graph.
I see, I see. So do we need some kind of layer-wise sampling strategy?
I think, that's one way. There's been a variety of, and I think there isn't one answer here. I think layer-wise sampling, I think adaptive sampling. I even think some approaches that actually introduce, more like skip connections and kind of global representations to let you bypass this tree structure in terms of computation can help. There's quite a few possibilities out there.
Okay, cool. Okay, thanks.
Hi, I had one question. So have you compared your algorithm or GNNs for isomorphism for some of the benchmark data sets, like some strongly regular graphs or bipartite graphs?
It's a good question. So because we know that GNNs are no more powerful or equally powerful as the WL test, there hasn't really been a lot of work done on benchmarking them specifically for isomorphism testing. There has been a fair bit of work on benchmarking GNNs for graph kernel tasks, right? Where we're trying to get not a strict isomorphism, but trying to get some kind of similarity measure. And their GNNs have been able to outperform more traditional kernel algorithms, but at significant computational expense, I would say, is the fair thing.
Okay. Thanks.
No worries.
Thanks a lot, Will, for the awesome
Thank you.
presentation.